So good afternoon, ladies and gentlemen, and welcome to the URail JU Innovation Days. So you are now connected to the session related to the cross-cutting activities. Before we dig into the interactive technical discussion, I would like to inform you about some housekeeping information. So as you see that all the microphones and cameras are muted in order to ensure that we fluid presentations. But of course, we are very interested to know your questions or comments. So you are very much invited to put any of your comments or questions in the chat, which are going to be checked during the session by my colleagues, and we will, of course, address them. So there will be three work areas presented today. So after each work area, there is going to be a question and answer session. So it's not after each presentation, but each work area. And you will be then invited also to, but you can put your questions anytime during the presentation. Please also know that the session is recorded. So in case you would like to camouflage your name, or then please do the necessary steps for that. We also have asked you to, after that, fill out a survey, so a questionnaire that you can provide your feedback on the event itself. And if you have any recommendations or suggestions for the future, it would be very much appreciated by my communication department. You can also subscribe to our mailing list if you go to the URail website. So today, today's CCA session, as I mentioned, it's covering three work areas. If you could go back to the previous slide, thank you very much. So the cross-cutting activities are focusing on areas which are not specific to one or to another subsystem of the railway system, but then these are overarching ones. So these are the ones that can be relevant for freight, for passenger, for infrastructure, or for rolling stock. Today, we are going to learn more what has been done in the integrated mobility management work area, on the energy work area, and also what has been done with regards to key performance indicators. As Carlo already mentioned in his opening speech, so there was the release 5 of the Shift to Rail high-level KPIs now presented to the governing board, and it's going to be also published in the annual activity report. So this, all the background information, how the model development, how the data collection has been done, will be presented today by the experts on this field. With regards to energy, it was also touched upon, and we all know that considering the current economic situation and geographical situation, it's a very important topic. So, of course, within this work area, the activities were not linked to developing or different technologies that improve the energy efficiency, but it was more to monitor the energy improvement potentials of the shift to rail innovations, as well as developing tools and standards in order to measure it in a harmonized way. And when we are going to the last point, but which is going to be the first subject of the today's session, and the integrated mobility management. So this work area is focused on providing different freight and passenger applications in order to have a better connection with the traffic management system, and also learn how the different applications can support and improve the TMS system for the future. So now I would like to, if you go to the next slide, you will see the agenda for the today's session. So as I mentioned, we are going to start with the I2M subject, and it's going to be chaired by Scott Heath, who is the Fine 2 project coordinator, as well as he's a key expert in the I2M work area. He has worked in the rail sector for nearly a decade, and he has 7 years of experience involved in EU-funded projects in both infrastructure manager and supplier organization side. As the current head of innovation and R&D for Thales UK Transport Division, he leads activities focused on urban and mainline railways, as well as big data systems that improve operation. He has passion for mobility as a service, is a cheerleader for the improvements of secondary railway lines, and an advocate for enhanced diversity and inclusion in the sector. So thank you very much, Scott, for leading the discussion on the integrated mobility management workstream. The floor is yours.
Thank you for the nice introduction there as well, Judith. I'll be quick on my introduction, and the main reason for that is I have 5 excellent experts teed up to talk about the work we've done in this work stream, and I guarantee that what they're going to say is far more interesting than just giving an overview. So if we progress to the next slide, I'll go straight into the details here. So in the work area 4.2, integrated mobility management, or I2M for short, we've been looking at 2 key streams of work. The first stream is looking at freight systems and really how we optimize freight operations in railways to make them more attractive to those who currently use road and hopefully shift their freight carrying onto the railway. We've been doing this in 3 areas. The first is looking at the interfaces for exchange of data, recognizing that if the systems work efficiently, then you're more likely to use them on the railway than the road. And a core part of this is the common data model that anyone who's been involved in Shift to Rail will know and have heard about quite a lot. The second facet is around dangerous goods management, recognizing that there's lots of items that are transported in the freight domain which require monitoring of their condition, ensuring that the temperature and pressure is monitored and adjusted accordingly. And the work that STS, as part of Hitachi, have been doing is really focused on that, and you'll hear more about their work. And the final part was around container management systems that us and Thales have been doing. And a lot of this activity is building upon the Impact 2 project, which closed out a couple of years ago, also in the CCA domain. The second part is around business services, and this was really looking at how we can improve the performance of the transport system as a whole, recognizing that for things like TMS to work well, you need an ecosystem that is performing well. So if you can't depart trains on time, you're never going to have success with TMS. So looking at the broader transport system and saying, how can we make this all run more efficiently and smoothly and bring the reliability that's necessary to have optimized transport. And if you optimize the transport system, you have better energy efficiency. And of course, you can deliver the benefits that systems like TMS really provide. In that section, you're going to hear a lot of proofs of concepts, and on my next slide, which will come in a second, you'll see some of the prototypes that we built there. The main thing also for me to highlight here is, as we've been talking about energy efficiency and how we optimize or reduce the amount of energy that's being used, it's worth saying that both of these streams are focused on that. With the freight system, you can obviously use more energy using the roads than you do using the trains. So by moving freight from road to train, we reduce energy consumption. And all of our business service is about enabling an optimized transport system that inevitably and ultimately will be more energy efficient. So both of these are really focused on actually how we do reduce the energy consumption inside the rail sector. As I said before, on the next slide, we have the list of prototypes. Those which are at the top are the ones that the experts will take you through once I finish talking, so I won't go into any detail on those. But the sections below in italics are the ones that we won't have the time to discuss today, but there should be lots of information appearing on our website fairly soon, and there may be other opportunities for us to talk through them. But it's worth saying that some of them are also very interesting. The very bottom one was looking at optimizing the bus network so that passengers who rely on public transport to get to railway hubs can have a quicker and more reliable journey. And that's been working with an SME, small business here in the UK, utilising their expertise with those of Thales. Other ones have been looking at how we optimize possession planning so that we reduce the amount of downtime. That has a big effect on freight operations and ensures that there's more available train paths for freight carriers. So there's lots of information available, and I hope to get more of that out to those people listening today. I don't want to talk anymore, so I'm going to hand over to our first speaker, which is Hannah from Thales. As I've said, and as been mentioned before, I'll be monitoring the chat, so if there's any questions that you put in there, I'll either respond to those by text if it's simple, or I'll hold it for the Q&A session at the end. But over to you, Hannah.
Hi everyone. If you could go onto the next slide. I'm Hannah. I joined Thales as a software engineer apprentice in 2017. Since then, I've worked on both large-scale engineering projects and smaller software projects. If you could perhaps go back one, sorry. And I worked on the Transport for Greater Manchester proof of concept as part of my final year university project and as part of the apprenticeship scheme. And that's what I'll be talking about today. So if you can go on to the next slide, please. So for those of you who are unaware, Transport for Greater Manchester is the transport passenger executive for Greater Manchester in England, and they're responsible for coordinating the various modes of transport across the area. So we have rail, tram, cars as well, and various other bus routes. And the main problem statement that they came to us with was, as an operator, I want to see the status of multiple modes of transport in one place so that I can focus on making effective reactions to incidents rather than searching through the data. So TFGM have a control center where they essentially spend a lot of their time trawling through various systems to discover incidents on the road and railway networks, and then try to effectively manage those incidents by disseminating information to various third parties. And if you could go on to the next slide, please. So the approach we made for this proof of concept, we tried to give it a very iterative process. So we talked to various members of Transport for Greater Manchester to understand the challenges that they had. So they had various automation challenges and integration. They didn't really have a very good live status of the network, and they couldn't really figure out how easily to notify other parties. So once we could understand the challenges, we'd then validate their understanding by coming up with plans and ideas of how to tackle these challenges. And then we'd design the solution, get feedback, try and further understand the challenges, and continue building on that. So if you can go next, please. So we did have initial customer discussions. Just before the pandemic, we did get a chance to go to their control centre in Manchester to understand how they work, their main tasks and what they do, and to understand what solutions that were already in place. So, for example, for manually raised incidents where maybe an emergency service would phone them up and let them know of an incident that was happening, they'd essentially store that information in an Excel spreadsheet and have a bit of a bootstrap UI on top, and that was how they were essentially managing those incidents. And so from that, we decided how we can sort of improve that solution and add more functionality to it. Next slide, please. So this was the output of a hackathon. So we spent about a week with various members of Transport for Greater Manchester to understand their challenges and the jobs that they had, what pains they had with their existing systems and what they were missing and what we could potentially add to that. The main output from that was circled in the green box. So what we thought we could perhaps add to their existing solutions, so we could detect disruptions and incidents better through various data feeds, automate some of those service disruptions and notifications, suggest some actions and responses, and integrate various other systems, because I think they use between perhaps 10 to 15 different systems to manage the network daily. We wanted to be able to make this information available to the wider TFGM organization and also deliver to other third-party applications. So next slide, please. So then once we'd figured out what we exactly wanted to design and perhaps add. We came up with some high-level designs, and this is sort of what we came up with. So you can see a map of Manchester with perhaps some heat maps or some highlighted incidents, and then a sort of menu widget at the side for the various different types of transport, so you could see what problems were currently occurring sort of in the wider area. Next slide. We then went and started to prototype various features. So we wanted to classify different types of incidents with a red, amber, green criteria. So we've done that with rail and the tram feeds. So there are APIs that exist sort of on the internet that we can pull in and based on specific criteria, classify it as an incident and display that to the users of TFGM. So an incident could be made more severe due to its location or for how long it's going on, or if it's overlapping with peak hours. You can sort of see via the images, we'd sort of put a marker on the map, and then there'd be a bit of information around the severity of the incident, where it was, if it was in progress, and what steps and actions had been taken to hopefully resolve that incident. So for the road network, we created a traffic heat map, and we pulled in data from Highways England and NTIS, which is the sort of UK road network. And we got some signal faults from Transport for Greater Manchester's Open Data API. Next slide, please. So yes, so for the rail, we monitored train departures from our Thales provided Darwin service, so we could identify which trains were running late and then create train-specific incidents. We could also then pull in some of the tram Manchester Metrolink data using Transport for Greater Manchester's existing open data API. So we could identify if there was no arrivals or departures for a tram stop, if the trams were running late above a certain threshold, and if the statuses of the passenger information displays were not updating. Great, thanks. If we could go on to the next slide. We also added some features to sort of further along incidents. So to notify wider management in Transport for Greater Manchester, we created a PDF just in their general procedure format for when an incident's ongoing. So if the system detected an incident, a user could then quickly generate and raise information and send that on to a wider audience. And here's an example of what our PDF looked like during the proof of concept. Next slide, please. So this was the end prototype from that hackathon. You can see we have a map with various incident markers all around Greater Manchester. Then we had a widget which you could open and close and search to view the various incidents sorted by the mode of transport. Thanks very much. Next slide. And we also had a couple of apprentices working on the project. So they added manual incidents, so you could manually add things to the map and not just pull in data feeds from the internet. Link out to social media, so you can see via the image that once an incident had been raised on the map, you could essentially hit a button and it would send out a tweet about the incident that was occurring. Another apprentice also streamlined the data gathered from the APIs, so it was a lot quicker and faster to get the information, and added events to the feed. So, for example, if a big festival or a big football match was happening, that information could be added and certain roads blocked off or information sent out regarding those events. Next slide, please. So how this solution benefited Transport for Greater Manchester, there was a lot more automation. It would allow quicker responses, so they'd spend a lot of time searching for incidents and then responding to them. This would hopefully remove that need to spend a lot of time searching for incidents, so the emphasis would be on responding to the incident or disruption that was ongoing and notify people in a much more effective way. And that would essentially help save energy for encouraging a shift to public transport from perhaps road users, which would be more energy efficient. And there was, the usual staffing and budgetary constraints that we had to work with. So we tried to address as many of those problems and sort of increase that operational effectiveness and improve the view they have and give them a more live view of the network. Yeah, that's everything from me. Thanks very much for listening. And I guess I'll be around to answer questions in the end. So back to Scott.
Thank you for that, Hannah. I can seamlessly pass over then to Marnum, who's got the next presentation, coming to us live from Germany and representing HACON and the work that's been done in Work Package 11. So over to you.
Hello, good afternoon. My name is Mahnam Saidi. I'm a research project lead at HACON. Today, I present a joint work with some of the partners of Find2 Top project, namely Siemens and Thales, that is related to interfaces for mobility management. Next slide, please. So before starting, for those of you who are not aware or not familiar, I give you a little background on the main enabler of this work, that is the integration layer. So in the Shift-Rail program, new traffic management functions were developed to improve the management of train operations, and the development of the integration layer initiated in the Interrail project and also was completed and developed further in the different Shift-Rail projects to integrate the developed and also external railway services with the traffic management system. It is essentially a common communication platform that allows integration of railway traffic management components with the traffic management system. It has a data-driven architecture with a unique language that is called the canonical data model. So the different systems may have a totally different internal data model, but they can still communicate with each other using the same language, and they should translate this data in the CDM format whenever communicating. The canonical data model provides data schemes for various layers, such as, for example, topology, timetable, operation, ATO, freight management, sandbox management, and decision support system. The data is arranged in topics, which is a collection of data objects that refer to the same element. So next slide, please. So the different systems can communicate with the integration layer using interfaces that consists of two parts. This communication, the APIs, that is the advanced programming interfaces based on REST or SOMP or Java, and the canonical data model that represents the data that flows through these advanced programming interfaces. These APIs were developed. The API was developed during the Impact 2 project, Israel 2, Israel 4, but also Find2. And in addition, in the Find2 project, appropriate classes were added, or appropriate paths were added in the canonical data model for validating the different models that were created in the project. For example, for conflict representation and detection and resolution, that was the topic of research by the Siemens mobility and the ETA calculation and distribution for HACON. Next slide, please. So a little background behind the work that I'm presenting. It's essentially, as I mentioned, the joint work or joint activity between the partners. And a little bit background on this work is that freight railways often suffer from unpredicted disturbances, which may be caused, for example, by extreme weather conditions. As a result, in order to control the effect or impact of these disturbances, sometimes temporary speed restrictions are put into effect. So currently, this process is done manually, resulting in speed restrictions being effective in larger areas than what is actually needed, or for longer durations of time that is actually needed. And therefore, one of the modules that was developed in the Find2 project, namely the prototype of Thales, dealt with this issue of deciding what temporary speed restrictions should be really put in place, and also with what duration of time. So using near future weather forecasts, These temporary speed restrictions were bound to, and also the area that they were put into effect were bound for a shorter duration of time than what was decided, that what would have been decided manually. But that's not the end. So we need to integrate this information in the forecast calculation to be able to provide a more detailed forecast to the people who will actually use this forecast. And this is the subject of the prototype that was done by Siemens for the conflict detection and resolution. As soon as this forecast is available, we need to inform this to the freight users of the system or freight management systems, because this would impact very much their operations in the sense of planning, for example, terminal operations, or informing the customers and so on. So this joint work, thank you very much. This joint work was enabled by the integration layer. So here you can see a high-level architecture of the whole system and the communication flow between the different modules and different systems. For example, the weather management system sends out the temporary speed restrictions to the integration layer, which are then imported by the traffic management system. As a result, the forecast is updated, and as soon as the forecast is available, the freight management services can subscribe to the integration layer for getting information about a specific train, or actually all trains, because the whole forecast is there. And then they can get the latest estimated time of arrival using the advanced programming interfaces that are developed in the Fine2, that are available from the ShiftRoll projects, and also developed further in the Fine2. Next slide, please. I think you're a bit too quick, so you should go back to the previous slide. Thank you. So here is a little bit more detailed overview of the weather management service. As you see, the external weather weather provider provides the weather forecast to the basically weather management service, and using that, it decides on the optimal temporary speed restrictions that should be put in place, and then they join a message queue and are sent, for example, then to the integration layer. Next slide, please. And then the conflict management service carries out the conflict detection and resolution and calculates the forecast based on the information it receives. An important feature of this is that multiple operators can work simultaneously on the same timetable, that is the master branch or master timetable, concurrently. And they can modify their own small parts of the network to produce a global solution. And also there could be a decision support system integrated as an additional player, either besides a user or an operator, or as a master branch. And then when the master timetable is decided, it is then communicated to the integration layer. So we can go to the next slide. And here we have the freight applications that can connect to the integration layer, for example, mentioning a specific train ID and train station. And then so for example, here you can see on the black, yes, this one, that for example, the yellow parts are where the temporary speed restrictions are active. And then the next one, please. As a result, you can see that the train slows down in response to the temporary speed restriction. And then this for sure has its effect on the forecasts or train run times. And the customers can subscribe through their application to the integration layer. And as soon as the forecast is available on the integration layer, here is a screenshot of this integration layer with the forecast that you can see. Then the customers can receive this information on their application with, for example, the representative stops and the arrival times of trains. So this was how basically a very brief or very general presentation of the different modules that were developed, and also a description of the advanced programming interface for freight management and conflict detection and resolution integration. And how we can use that in order to actually minimize the impact of extreme weather conditions on the whole train operations. So this was a presentation, and I would like to thank you very much. And I think if there are any questions, we can be there for the Q&A session.
Thank you, Marlon. I think you managed to do that with a minute spare as well, which is exceptional in this situation. So to keep us slightly ahead of schedule, or at least on it, I'll seamlessly pass across to Steve and let you give your presentation. You need to unmute, Steve.
Steve Sykes from Thales. This presentation is about what happens when the rail network is congested. So I'd like you to imagine the rail network in a really bad day, where the trains just haven't been able to meet their schedule. All the passengers gather around the signboard. And in the UK, the signboard is provided by Thales. And on a normal day, that signboard carries good and useful information that will help the customers to get where they need to be. But when the train network is having a bad day, then that signboard information isn't necessarily stable. So it might tell you your train is going to arrive at 12:05. Then you look again in 5 minutes. Oh, the train is going to arrive at 12:10. And you look again in 5 minutes. Oh, the train is going to arrive at 12:15. And the numbers keep shifting. And that's because of the way the existing algorithms work. The task for us was to do better than that, to make an improvement, if you like, over what Thales already provides. And the way we've done that is we've made a simulation of the trains on the network, with the aim of using that simulation to predict when the trains will arrive at their destinations. And there's a little picture there that shows how it works. Each section of track that only allows one train, that's called a berth in the UK. And there you have a little sequence of trains, a little sequence of berths rather, numbered n-1, n+1, n+2. And each berth is protected by a signal. And on entry to a berth, there's a signal that tells the driver if he's allowed to proceed, and also whether there are any trains ahead. So on this particular occasion, they have a train being told that there's already a train in n+2. That's called preliminary caution, and the train driver has to slow down. So what we need to do is make a simulation that takes these. So because the train driver is told where the train ahead is, that creates interactions between trains, and that is why trains tend to slow down when they are bunched up, and that's what we're trying to simulate here. It's a slightly more detailed summary at the bottom of the slide. Now, thank you very much. Context diagram, yes. So we have two parts of our work. We have an offline processing algorithm that takes data from the train describers and computes statistical models for the length of time across each berth. And then we have an online processing part that makes the predictions happen in real time. Next slide, please. I'm not going to obviously go through all the details of how we did it, but this is just to show some of the contents of what we did. We used a fresh air distribution to model the time taken by a train across each berth, because that just empirically fit the data well. We used something called a generalized linear model, which is a regression technique that uses explanatory variables that control the model parameter, so that you can take things into account. You can take into account the time of day and such like, and then what the occupancy of the forward berth were in making your model. And in order to choose between models, we use something called the Akaki information criterion. So we generated lots of candidate models, and we used the AIC to choose the most appropriate one. And what that does is it selects a model that has the right amount of parameters. So if you have a lot of data for a particular berth, then you can have a model with lots of parameters. If you haven't got so much data, then it's better to have fewer parameters in your model. So you balance the size of the model compared with the size of the data. And that's a method that has roots in information theory. It's quite a deep model. Next slide, please. So what does our model currently know and not know? It currently knows how the speed of a train depends on the signals last seen. It knows the time of day. Our model doesn't yet know what the schedule is, and that's important because the schedule can be a major driver of the performance of behavior of trains on a network. But it was within the scope of the project, it was difficult for to bring that information in for technical reasons. We don't yet know when the driver is required to take a break, which is another important thing. It's known within the rail system, but it wasn't part of our project, and how fast the train has gone previously. So there's a number of things that could be used to improve our estimates, but that's future work. It's reasonable to say we start with something that works and makes an improvement over Darwin, but if you want to make it better, well, there's always ways of making the modelling better. Next slide, please. So this is an example of our results. On the x-axis, we see the prediction horizon in minutes, and on the y-axis, we see what the error was at that particular prediction point. Prediction horizon in minutes is got 0 on the right-hand side because that's when the train got to its destination, and so -60 on the left-hand side means you're predicting an hour in advance. This particular example is for a train on a bad day. Well, clearly that was our interest, find bad days in the network. This particular train has been held up by traffic, quite a few trains, they're all bunched up. And our models know how that works. They know that when the trains are bunched up ahead of you, the trains are not going to be able to keep up at their normal speed. And so it gives takes that into account, and it gives quite a good prediction. So the defined 2 predictions are the ones in boxes. And you can see that our first prediction is at 20 minutes before the train gets to its destination, and we converge on the true time from there. The existing algorithms, the Darwin algorithms, they don't do quite so well because they're not modelled, they're not designed to take the interactions between trains into account. What they do take into account is the schedule. So in a lot of cases, Darwin has an advantage on us, but when the rail network is congested, then the fine-tune prediction does a little better. So there we have 6-7 minutes improvement in accuracy, and that's worth having. Next slide, please. So here we have an example where the existing Darwin predictor is better than what we have produced here, because the algorithms we produced so far don't include the schedule information. So and what that means is that our algorithms think the train can just whistle through the network, but if the schedule says no, you must wait, then our algorithms don't currently take that into account. So it's something for future work is to bring those two together. Next slide, please. So we have conclusions. The results are quite good. So we've succeeded in our aim of making a prediction that's better than Darwin when the trains are bunched up. And it's implemented in a way that we can scale it up to full-size operation, because we built on something we've used at Thales before, which is called a discrete event stimulation architecture that can be distributed across multiple machines. So implementation at scale is not really a problem. And Thales GTS plan to carry on. They plan to, so we've done a proof of concept, and the team now plans to refine the system and begin the process of incorporating that into day-to-day operation with Darwin. And if it's successful, that will improve the quality of data for rail network and for digital planning tools that are also used from the network. That's all I have. So thank you very much, and I look forward to hearing any questions later on.
Thank you, Steve. I think you actually trimmed a minute off Marnham then, so the gauntlet has been laid. Thank you very much. So next up then, it is Claudio and Andrea, who represent Hitachi Rail STS over in Italy. I can see one of you has appeared. I think it's Andrea. Yep. So Andrea, I'll hand the baton to you.
Thank you. Hello, everyone. My name is Andrea Garrone, and I've been working in Hitachi for the last 2 years and a half. I started my journey here as a researcher in the field of artificial intelligence for the railway, and since 2022, I've been holding the position of automation engineer. Today, I will present you the work done together with my colleague Claudio Cavalletti within the work package 12 of the Find2 project. So next slide, please. Okay. Find2 work package 12 is concerned with developing a prototype for the management of dangerous goods in the railway, and the main goals here are improving the safety level of freight trains while transporting dangerous goods, reducing the maintenance costs and increasing the system availability by introducing condition-based maintenance interventions, improving the freight trains logistic management, and finally, let's say, exploiting the data structure developed in the canonical data model of Europe's rail. Next slide, please. Okay, what you are seeing here is the high-level architecture of the developed prototype. The system consists of two main blocks, the DGMS, which is the Dangerous Goods Management System, and the TMS, both composed of multiple microservices exchanging data through the integration layer. Next slide, please. The DGMS is composed of multiple subsystems. The most important one is the onboard control unit, which is, let's say, able to get the data from a series of sensors installed on the freight wagons, as you can see in the figure, and communicate with the TMS through the integration layer. Next slide, please. Okay, the data is published on the integration layer, exploiting the shift-to-rail canonical data model. In particular, for this prototype, we developed an integration layer that is able to manage both CDM STS messages and CDM shift-to-rail messages, and which is able to facilitate the let's say, asynchronous communication among the microservices. Next slide, please. Okay, within the TMS module, there are two main components, the AMA, which stands for Anomaly Management Application, and the HMI. The AMA is responsible basically for taking decisions based on the data, and all the decisions are taken according to a decision matrix as the one that is showed here. Next slide, please. While this one is the HMI, which is composed of four main sections. The one in the top left showing all the alarms received together with a timestamp and the alarm type. The one in the top right that shows all the observations received by the master control unit and acquired by the sensors. These sections highlights possible anomalies with different colors and allow the user to click on a specific observation and see the message in the shift-to-rail CDM format. The third section, the one in the bottom left corner, shows the train's path in real time from the origin station to the destination station. And finally, the last section shows the timetable graph highlighting the scheduled and the actual timetable. Next slide, please. Okay, the following slides show the main use cases that, let's say, prove how the objectives have been achieved. The one you are seeing now is the first use case in which an axle box temperature alarm arises. So basically the onboard control unit sends the alarm to the TMS that sends a message to the train ordering to stop in order to avoid possible damage or derailment. And we can say that this use case demonstrates how the use of the prototype can improve the level of safety of the freight trains carrying dangerous goods. Next slide, please. This is the second use case in which an axle box temperature warning arises. In this case, the onboard control unit sends the warning observation to the TMS that sends a message to the train ordering to slow down in order to lower as much as possible the temperature of the axle box. This event in particular highlights a problem with the axle box, meaning that the axle box needs to be maintained as soon as possible. Therefore, it demonstrates how this prototype can be used to introduce condition-based maintenance interventions, reducing the maintenance costs. Next slide, please. Okay, for what concern the objective related to the improvement of the logistic management, what we can say is that the developed prototype can guarantee the continuous transmission of the GPS signal of each wagon, providing real-time localization of the freight wagon fleet. Next slide, please. Finally, we are compliant with the data structure developed in the canonical data model of Europe's rail. As already said, we developed an integration layer that can manage both CDM STS and CDM shift to rail messages, and can easily manage the communication among the subsystems. Next slide, please. Okay, to conclude, we can say that the prototype developed within the WP12 is able to minimize the risk of accidents during the freight trains transportations. It is also able to monitor different parameters, for example, axle box temperature, making it possible to introduce condition-based maintenance interventions. It also provides GPS localizations, which is very useful for managing the freight trains logistics. It publishes data on the EL, on the integration layer, which ensure, let's say, future compatibility with other partners. And finally, an important, let's say, energy saving aspect is that the power consumption of these devices composing the prototype, so the master control unit and the sensors, is relatively low, meaning that they could be powered by energy harvesting systems such as solar panels or also piezoelectric energy sources, and this is a quite good aspect for energy saving. So next slide, please. Okay, so the prototype has been developed, has been concluded in July and successfully tested in October. In order to present the prototype at InnoTrans, we also realized a video, a demonstration video, which is available at the link that you are seeing in the slide. And all the technical details are available within the deliverable to 12.2. So thank you all for your attention.
Thank you, Andrea. Continuing the trend there of under 10 minutes, which we appreciate. If I could get you to paste the link into the chat, that might be easier for people who are interested in seeing your video as well.
Of course.
Thank you. Okay, great. Our last presentation is from Matt. I can see you on the screen, so I'll hand it straight over to you.
Yeah, good afternoon, everyone. My name is Matt Allway. I'm a solution architect here at Thales UK. Been here for about 9 years, working on a range of things under the heading of some digital railway. I will start with a brief apology. I'm presenting someone else's slide pack today, so the content of this will be as exciting for me as it is no doubt for you. If we could have the next slide, please. So we looked at integration between a traffic management system and a stock and cruise system. Stock and crew was voluntarily provided by our partner IVU. They're keen to see how these systems can work together too. So good example of cooperation between different players. And what the approach we took, very much in keeping with sort of other projects that are presented today, is really to allow each system to play to its own strengths. So IVU provides what is essentially a resource management tool for trains and train staff. Traffic management provides a resource management tool for track access and routing, and each system has its own data and view of the world, but the common purpose is to match a resource demand to a plan and to forecast against that deviation. So if we go to the next slide, please. What we did was essentially utilized a shared forecasting methodology. So we took it from our existing message catalog in the interest of speed, but you could use any sort of common shared messaging format. The beauty of this really is that as each system can be as proprietary as it wants internally, and externally as you're sharing your conclusions, not your workings, in this case forecasts, each system can sort of operate independently and you avoid a vendor lock-in. So in the examples we'll show today, traffic management essentially sending arrival forecasts to a stock and crew system responding to those events, and allowing the traffic management system to reforecast the train plan based on that. So if we go to the next slide, please. And if I can ask you to click start on the video, we really will be testing the technology now. Here we go. Yeah, I think it's going. Yeah, so this is first scenario, which is essentially entirely isolated the traffic management system to begin with. We have a railway constraint, and the TM system would have no way of knowing about this. So here we can see how the IVU can identify this constraint and update traffic management based on the shared data model, which is train forecasting in simplest terms. So hopefully you're going to see all the magic happen in front of you. I apologize if that's not quite big enough. But show how distributed tools can work together, provide a common vision. So you can see here now that Aramis has received an update. Well, you will see Aramis has received an update. There it is. And then the traffic management system can act to do what a traffic management system needs to do and resolve the conflict. And then that information can be reflected back into IVU. And the stock and crew can reforecast or reschedule as required based on the optimal solution to that. There's also quite a good advert for our traffic management system. As you can see here, the smaller purple boxes, you're seeing basically a progressively reducing conflict based on sort of the operational tolerances built into the network. Spot the theme, message passing back and forth. Yeah, and you can see now essentially that we've resolved the situation in both systems, and each system has only needed knowledge derived from its world. So you can protect those things that need to remain proprietary and without exchanging masses of data that's not relevant to other systems. If we go to the next slide, please. Yeah, so if you could click play again. And again, a very similar model here. In this case, the constraint is derived from the trackside infrastructure as opposed to the stock and crew. Again, we'll be able to using this common forecasting model, we can supply this information to the stock and crew system. The stock and crew system can use that to identify problems in its ability to resource that plan. One of the nice things about this example is we can see the way this can scale up from individual train-related events to something that's derived from a trackside infrastructure constraint, i.e. knocking out a temperature speed restriction that affects multiple trains, and how that can quickly be conveyed to downstream systems to which that information is relevant. So you can see pretty quickly what a catastrophic effect that can have, and it allows the operator to essentially start responding to events at scale, as opposed to having to manage this sort of sequentially. I think that might be the end of that video. So if we move on to the next slide. It's the same slide. There we go, magic. Yep, and if I could ask you to click play on that one. And so this is where we've got inputs into both systems sort of happening at the same time. So traffic management system will observe a failed train. The stock and crew system will observe a failed train, and those different effects need to be integrated up into a sort of coherent picture. Again, this allows the systems to swap information based on that common understanding provided by forecasting, to understand the impact on the train plan. So again, one of the nice things sort of highlighted there is that very application-specific constraints being applied. So a deployment restriction in the stock and crew terminology, and in terms of how it responds to that, is not particularly relevant to the traffic management system. It doesn't need to see the workings; it only needs to see the outcomes. So we can see how we can make interoperability sort of commercially viable and allowing people to protect their own IPR and the unique capabilities that different suppliers can bring, while still working together collaboratively to deliver the railway. So yeah, so the traffic management system would have really no way of knowing that a spare vehicle was available and switched off in a siding nearby, whereas this is available in the stock and crew system. So we can see how the train plan can be updated based on entirely new vehicles, which is not within the scope of the service plan. So we can see now how the introduction of that new vehicle creates demands on the track infrastructure in terms of bringing it into service, and the traffic management system can now usefully resolve that. I think that's the conclusion of that video. So if you'd like to go to the final slide. Yeah, so I think hopefully you've enjoyed those demonstrations. We've shown how common messaging can integrate disparate systems efficiently using simple and common APIs is the most efficient way of achieving this. And although we did not use the CDM model, obviously this shows its applicability. If I've breezed over anything, people wish to ask questions, then please do so in the chat, and I'll do my best to answer them. But with that, it's back to you, Scott.
Thank you, Matt. I was going to say one thing that's also worth highlighting of that last use case is the state of the art, which at the moment tends to be people telephoning one another from the two services, so someone who's managing operations and someone who's managing the trains, or slightly more advanced people in the same office being able to shout to each other. So one of the biggest advantages here is that seamless message exchange, just sort of highlighting that as well. And yeah, you're right, although we didn't use the CDM in the kind of live format, we did use an analog of it. So it's a true demonstration of the CDM. We used the right messaging. It's just we hosted that locally as opposed to using a cloud solution that was subscribe and push. But thank you, Matt. I'm looking at Judith to see how much time we've got for questions, and also looking at the community to see if there are any questions. At the moment, there are none in the chat space.
Yeah, I haven't seen any, but you managed perfectly the time. I mean, all the speakers, so thanks a lot. I think it also shows that how important the I2M activity is, that having all this application linking to the TMS, and then the use of the CDM exercise, yeah, so that we have harmonized and commonly agreed methodology, which helps then to have all this interoperable application included in the TMS. So it's thank you very much for all the presentations of all the applications that has been done in I2M. And I didn't see any questions, so then I would suggest that we go to the next work area. Thanks, Scott, and also for the colleagues for the interesting presentations. And then we would move on to the energy work area, which I said that this work area was mainly focusing on tool developments to define a harmonized methodology to calculate the energy consumption of the rail system, and also to assess the potential energy reduction potential of the shift-to-rail innovations. So, and then Michel, who is the work area leader of energy, is going to give us an introduction. So he has been working at Alstom since 1996. He has worked in the field of power electronics, power converter, traction chains. He is currently an expert on energy and innovation, and involved in definition of the new generation of hybrid trains, battery or fuel cell. He is also involved in the FINE2 project, and as I mentioned, that he is the work area leader of energy. So Michel, the floor is yours. Thank you.
Good afternoon, everyone, and thank you for the introduction. So the shift to rail energy saving that we are going to show here come from the programs FINE1, FINE2, and OPEOS that have been run these last years. The main objective of these programs are, first, to develop energy calculation methodology for rolling stock and implement an energy calculation tool that have been developed with the project OPEOS. The second objective is to set an energy baseline as a reference for all system platform demonstrator in the segment high speed, regional, urban, and freight traffic. The third objective is for every SPDs to define operational scenarios to calculate the energy KPI. Main energy KPIs are train energy consumption per kilometers, and for passenger train, energy consumption per kilometer passengers, and for freight train, energy consumption per kilometers and tons. The fourth objective is then by injecting the improved characteristics of product demonstrator of shift-to-rail in OPEUs to calculate the energy saving for the reference baseline. Next slide, please. I will present the energy calculation and simulation methodology. Then Jürgen will present our estimation of energy savings due to shift-to-rail innovation. Then Silvio will give a view on innovative solution to save HVAC energy in BEMU. HVAC is heating, ventilation, and air conditioning. BEMU is a battery electrical multiple unit. And Jürgen will conclude on an outlook of additional saving that are foreseen in EU rail flagship projects. Next slide, please. So the methodology to compare energy saving is to define for every SPDs an equal service profile and define the classic traction system, for instance, IGBT converter and induction motor, and the future technologies, for instance, SiC converter and high-speed axial flux motor, and by simulation with OPEUs, quantify the savings, assuming, of course, that the technical improvement reported by the TDs are applied. Next slide, please. The input for energy baseline is speed profile with line parameter, timetable, gradient, speed limit as defined in IEC 59591. The reference simulation data consists of vehicle, line, and traction component parameter. We see here an example for a line converter as a function of power, and the speed profile for regional as a function of kilometric distance. Next slide, please. The traction topology for EPUs is globally defined for the full train and divided in power subsystem or power components with a central part that is shown here as absorption circuit. Another naming for this part is DC link or DC bus. On this DC link, the main loads are traction equipment, auxiliaries, and rheostat for braking energy dissipation. The source is here catenary, and in this topology, we have energy storage system with battery or supercapacitor. For a demand in power at wheel and auxiliaries, OPEU's tool calculates the energy flows between these elements. Energy flow is the power, in fact. Next slide. All that I have explained before is implemented in OPEU's tool. Track data, train data, operation data are entered with an Excel interface, and output, the results of the simulation, are also in Excel format. Simulation structure is implemented in MATLAB and Simulink, as well as the component model library. Next slide, please. In FINE 2, we calculate the global energy saving at train level with the new technologies developed in Shift2Rail. Many of these technologies and implementation are confidential, as required by the partners. It is why I want to illustrate with some concrete example the potential of energy savings. First, energy consumption of rolling stock can be divided in three main parts. The first is energy at wheels that makes, in fact, the train moving, and mainly comes from the resistance to motion forces. The second is energy losses in all the power subsystem or on power components. And the third is the energy consumed by auxiliaries. There are two types of auxiliary load, medium voltage auxiliaries and low voltage auxiliaries. The main consumers load are air compressors for brakes, HVAC, and cooling device for traction equipment. Now the introduction of new component and new architecture is the main lever to reduce energy consumption. It's why I show here an example. It's an example to improve the standard traction drive supplied by 1500 volt DC with induction motor and IGBT 3.3 kV converter. Moving to a traction drive architecture on a 1000 volt DC link with an input DC-DC converter made with medium frequency transformer and dual active bridge with SiC MOSFET 700 volts component and a high-speed axial flux motor, we can save 20% energy on all VEMUs, whatever is the mission. The input data for this calculation comes from published data on products existing in other domains. I mean in power semiconductor, in aeronautics, and in automotive. In addition, as you can see, if we can directly connect the batteries on the DC bus, the saving can increase to 40% compared to non-recuperative catenary. This is often the case with 1500 volts DC. So this is the first main lever for energy reduction. For energy at will, in high-speed segment, there is a potential of more than 20% saving by improved aerodynamic design, drastically reducing the resistance to motion, especially in tunnel. Weight is also one of the main contributions to energy at will. You see here the value of reduction of energy at will function of the weight reduction. You see, if we decrease 1% the total mass of the train, we reduce by 0.8% the energy consumption. Eco-drive can also be a contributor, but with a lower impact, not exceeding 10%. For auxiliaries, new HVAC technology will bring improvement as it will be described later by Silvio. Suppression of air compressors, airless train, we call also that airless train, and replacement by electric friction brakes is also another lever for energy reduction. And finally, a better control on energy monitoring is the last lever for energy reduction. I can just give a live example. When I discussed with an operator, tram operator, he told me, if you want to reduce the energy consumption, please make train with very rapid conditioning by control command in the morning. Therefore, the driver will not let the power on during all the night. Just to say that by monitoring the energy consumption of all components in all modes, I mean conventional commercial service with passenger, commercial service without passengers, or parking mode, we can retroact in real time by smart control of auxiliaries. So this is just an overview on the next slide, please. Now I will let Jürgen to go on energy saving due to shift-to-rail innovation. Please, Jürgen.
Yeah, hello everybody. And my name is Jürgen Ernst, and I'm an electrical engineer and I've been working for Deutsche Bahn for more than 25 years. And my main subject is the overall railway system. So I'm not an expert of a special subsystem. So I look at the overall railway system from an operator and from an infrastructure manager view. So now we start with energy savings due to shift-to-rail innovations. And as Michelle already explained, there are 4 measures to reduce energy. The first of all is the reduce of energy losses of the traction chain. The second, reduced mass. The third, the improved control strategy and operation. And last but not least, improved aerodynamics. And now here you see technical demonstrators developed in Shift2Rail and how they contribute here to energy saving here. These are first in this slide, these are only demonstrators for passenger trains here. And the first one in the traction system here is the silicon carbide converter with reduced losses in the traction chain. You see this on the left-hand side, you see this picture of such a converter. And the very important is to mention that we not only reduce the loss within the converter, but also losses are reduced within the transformer and the motor, because the harmonics are reduced due to the higher switching frequency. And this innovation is already ready for application, and it's the next column there. It's suitable for refurbishment. So you can refurbish old trains and change the converter to new technology in order to save energy. And in Shift2Rail, it was developed for a regional train, for metro and a tram, but the technology can be applied for high speed as well. And the next innovation, it's from Talgo. No, not. Okay, perfect. And it's the gearless permanent magnet synchronous motor. And you see the picture on the left-hand side, and it's integrated in a Talgo high-speed train, and it will reduce further the energy consumption there. Certainly, it is not suitable for refurbishment because all other trains are different. And even if you want to apply it for regional or metros, you have to do a lot of innovations to use it there. But it's worth concerning the energy saving there. We know it from the automobile sector that already such technologies are state of the art. Next one is the car body with a light composite material. The left-hand side, you see the car body, and partly it's ready for application. And the very, very important is that you can save a lot of mass and therefore reduce the energy. You can apply it to all traffic segments there. The same for the running gear with reduced mass. And then you have the brakes. In Shift2Rail, there was the airless electromechanic brake developed. It's not ready for application, but it will finalize soon. Certainly not suitable for refurbishment. And yes, and last but not least, you have the HVAC system, the heating, ventilation, air conditioning, cooling system. There was a new technology developed with a natural refrigerant, CO2, and with an integrated heat pump. Everybody knows it from the home, where it's a new heating technology, and it reduces the energy consumption. You see the picture on the left-hand side. And the next slide. And this, now I come to the freight trains. There are several innovations, especially the digitalization concerning automatic train operation with energy optimized driving. You know, these driver assistance system, which gives information to the driver how he can drive optimally, but not all drivers do it, and therefore the automatic train operation can improve this. And it's suitable for refurbishment too. And then in IP5, there was a connected driver assistance system developed. That means that the train driver gets also informations from the infrastructure side. So where is the next train ahead? I think it's similar to these activities here already mentioned in the previous I2M activities here. Yeah, and then we have on the wagon side, there was a wagon developed for high-speed freight traffic. It's called Extended Market Wagon, and it's for the future. So you can transport fruit or vegetables or something like that much faster than today wagons. And these wagons have improved aerodynamics, and that reduces energy. And last but not least, on the wagons, there was a study carried out by DLR concerning optimizing container sequence. Because nowadays, the containers, there are loaded wagons and non-loaded wagons, and all mixed together, and that has a very poor aerodynamics. And if you sort them, you have first the loaded and then the unloaded wagons, then you can decrease the energy consumption. And last but not least, we have also the silicon carbide technology for locomotives. Now to the next slide. I will come to the infrastructure and control and command system here. Again, ATO, I also already mentioned it. Yeah, and certainly the traffic management system here. I think it was already mentioned in the first session here. And last but not least, there was an innovation it's called smart power supply, where it's for 50 Hertz networks. There usually you supply the train only from one side. And that means that it's not optimal. And therefore, the idea is to supply them with a converter substation, so you can supply the trains from both sides, from the right and from the left-hand side, and therefore you can reduce losses on the overhead line, or you can increase the substation distance here. And it's suitable for countries where you have this 50 Hertz supply. And now to the next slide. And now you see the energy saving potential in figures here for passenger trains. And you see the largest savings are possible due to the innovations in traction, certainly for regional traffic and for metro, because they accelerate and stop a lot. So because the distance between the stations is low, and the energy saving for high speeds trains is a little bit lower. Yeah, and the car body contributes a lot to energy saving because it's much lighter. Running gear and brakes has a small impact, and HVAC looks very low, but concerning with relation to the HVAC system, the energy saving is higher. And for freight trains, yeah, connected driver systems has a low impact, and the silicon carbide converter. But you see the extended market wagon with this improved aerodynamics and the optimized container sequence has a huge impact on energy saving. So it's really important to look at these innovations here. And here you see the total energy savings here. And for the different traffic segments here. And you see that I separated into short term for refurbishment That's very interesting for railway undertakings to do innovations, to refurbish their trains or the infrastructure. And here I report the long-term saving. The hugest savings are of freight and regional. Now I come to the conclusions. So you've learned that several energy-saving technologies are developed in shift-to-rail, and the technologies suitable for refurbishment can use the short-term energy consumption by 4 to 20%, dependent on the traffic segment. And these are, for example, the silicon carbide converter, the connected driver assistance system, and ATO, and optimized container sequence. And with new trains, the long-term energy consumption can be reduced by further 4 to 30%. And for some technologies, the energy saving potential still have to be estimated. For example, for these substations with converters. So thank you very much for your interest. And now we come to the next presenter.
So the next presenter is Silvio for innovative solution to save HVAC energy in BMUs. Please, Silvio.
Yeah, thank you, Michel. Yeah, hello, my name is Silvio Donna, and I'm working at the DLR at the Institute of Vehicle Concepts, and worked at Fine2 on new HVAC energy saving concepts. Yeah. The study is intended to help to reduce the energy demand and those the CO2 emissions, and to increase the range of the battery electric multi-unit short BEMU. For this purpose, various measures around the HVAC, heating, ventilation, air conditioning, are considered. Next slide, please. The overall concept, thanks, is to combine the OPIUS tool already shown for the longitudinal dynamics with the DLR model for the thermodynamics of a car body. The approach is iterative. Results from one tool are used as inputs for the other, and so on. The whole procedure is based on the norm EN 5591. Next slide, please. The car body model is described as a regional battery electric multiple unit car body through various wall and window elements, passenger model, etc. This model has been validated in Fine2 task 4.2. The results are shown in deliverable 4.2. Next slides, please. The inputs are based on the BEMU baseline, which you can find in Fine2 D 2.2 and on the EN 5501, which includes the service profile, which you can see on the right, on the top, and of the regional train, and also the operation points that characterize the thermal car body model. Yes. Next slide. Yeah, first, the EN 5591 operation points have been analyzed, and the most demanding operation points have been identified. The operation points with high or low ambient temperature are the most demanding in terms of HVAC energy demand. The table on the left side is with these operation points And on the right side, there you can see a graphic with the traction and the HVAC in blue. And yeah, you can see it for all the investigated operation points. Yeah, next slide, please. Yeah, the BMO baseline is defined with the heat pump because it is expected that all future BMOs will have heat pumps instead of conventional HVAC systems. The study evaluates the higher demand of a conventional solution with resistance season to demonstrate why heat pumps are regarded state-of-the-art for all future BMOs. Next slide, please. The measures and main concepts to reduce energy demand are measure 1, heat storage. With this technology, the heating energy demand is provided by a thermal storage instead of using electric energy from the battery. The measure 2 is the improvement of insulations, and they lowers the heat losses through the car body walls. And last but not least, the measure 3, the reduction of the HVAC energy demand by utilization of the full temperature range of the EN 14750. And now we want to come to results. Yes. The main results in terms of additional range for each OP are, at first, the heat storage is very effective in heating operation points, but ineffective in cooling operation points. The heat storage provides a maximum of more than 9% range increase in some operation points. The second result is that the improved heat transfer and utilization of full temperature range are effective in heating and cooling operation points. And the third, for the measure 2, for measure 2, maximum range increase is slightly more than 2.5%. And for measure 3, the maximum range increase is slightly more than 1.7%. To compare and benchmark the difference measures, the yearly energy savings compared to the BMU baseline with heat pump have been calculated for the climate zone 2, according also again for the EN 50591. Next slide. Yeah, now I come to the second results slide. First of all, as previously announced, the conventional heating with resistor heater is compared to the heat pump solution. It shows that yearly energy demand would be 5.3% higher without the heat pump. Therefore, the heat pump is the most promising technology. For the other measures, the yearly energy demand can be reduced by 3% with measure 1, the heat storage, and by 0.6% to 0.7% with measure 2, the heat transfer, and measure 3, the utilization of a full temperature range. Finally, it should also be mentioned that the implementation of measure 3, the utilization of a full temperature range, requires lower effort than the other measures. Therefore, in principle, measure 3 could also be implemented in already running vehicles, while the other two measures are preferably for new vehicles. All the results are documented in the FINE 2 deliverable D4.3, which will also be publicly available through the official project website. So Thanks, and thank you for your attention.
Thank you, Silvio. Now the outlook by Jürgen. Please, Jürgen.
Yes, the next slide, please. Yeah, the conclusion and further steps here. So you learned several energy-saving technologies, and Michelle mentioned a simulation tool that was developed in Shift2Rail. It should be stated that this tool is public and can use by everybody. So that helps to integrate it or to use it for all stakeholders there. And the technology suitable for refurbishment can reduce the short-term energy consumption by 4 to 20%, and railway undertakings and infrastructure managers should carry out a cost-benefit analysis to clarify whether refurbishment of existing trains is economical. For example, to change the HVAC unit or to update the converter to the new technology. And energy-saving technologies for new trains should be considered in the tenders of the railway undertakings, and certainly then they will be realized by industry. And if they are not considered in the tenders, there might be the problem that industry is not going to realize these technologies because the saving is on the operator side here. But further technologies for energy saving have to be further developed there. Now I come to the next slide, yes, and outlook on Europe's rail. And the following energy saving topics are foreseen in the EU rail flagship projects to achieve a higher TRL. And the energy saving potential should be estimated by means of a demonstrator in real operation. Because only if you have a real demonstrator and you can show it in real operation that you save this energy, then railway undertakings are going to invest in these technologies. And technologies that are further developed in Europe's rail is first of all the automatic train operation, the energy optimized driving in flagship project 1, 2, and 6, the traffic management system to allow smoother traffic and less unplanned stop. It's in flagship project 1 and 6. And yeah, we already learned a little bit about that in the other section there. And here is the idea is to really to apply it, to bring it to a higher technical readiness level that you can see really that you can save energy. And certainly the substitution of diesel trains by battery and hydrogen powered trains developed in flagship project 4. And yes, I already mentioned this electromagnetic brake, the airless brake, but this gives only a very small energy reduction, and you can have a higher energy reduction if you have a total airless train, because then you don't need all these air tubes there, and you don't need the compressor, etc. Air is not a very good actuator for this railway system, but then you need an airless suspension, an airless pantograph, and airless door driving system here. And these technologies are also developed in flagship project 4. So, and last but not least, HVAC solutions with alternative with natural refrigerants are also further developed in flagship project 4. So you see, we will do a lot in Europe's rail, especially flagship project 4, on further energy saving. And yeah, I'm happy that this was integrated into Europe's rail. And yeah, we were going to develop it with the same industry partners. But in addition, there will be a lot of other railway undertakings and infrastructure managers involved in these projects as well. So I think it's a good opportunity that they are going to apply then these new technologies. Thank you very much for your interest. Oh, I forgot. I have a further slide here. Not all these ideas that I mentioned before are covered in Europe's rail here. And for example, the most important topic concerning freight, the lighter wagon with improved aerodynamics, the extended market wagon for intermodal trains. It's not covered in Europe's rail and still has to be figured out how it can be further developed. And the second innovation there, the optimized container sequence, is not covered there. And further technologies under the saving of heating and cooling for battery and hydrogen trains. Yeah, was Silvio already mentioned here, that they are not covered by Europe's rail up to now. So there is still a potential for further research, but in Europe's rail there are several calls, so perhaps we can integrate it into one further call. Okay, now I thank you for your interest.
Yeah. So, question. There is no question in that have been asked during the presentation. So, are there some questions?
No, I think I don't see any questions either. Thank you very much for the speakers, and I think this overview slides were very interesting and summarizing really the situation clearly. Also, that we can see that there is a significant potential energy reduction possibility already implementing the shift to rail innovations into the European railway network. But of course, we know that we can do more, and we can see and we should assess what are the most promising technologies in order to further improve the energy performance of the rail system, in order to make rail even more competitive compared to the other modes of transport. So this is, as we know, the energy bill is a significant part of the costs for railway undertakings. So having a better, more optimized energy usage and more energy efficient technologies are key for the sector. So thank you very much, Michelle and Jürgen, for the interesting presentation, and also for the other speakers presenting what has been done in the work area energy of CCA. And then we would move to the last work area of today. It's last, but it's a very, very strategic and important one as well. So it's the KPI work area. So this work area was tasked to assess the high-level KPIs that were identified in the shift to rail regulation. So life cycle cost, capacity, and punctuality or reliability. So I would give the floor to the work area leader, Michael Meyer-Zuhörster, who is a chief engineer of the Institute of Transportation System and has joined the DLR in 2001, bringing already 6 years of railway research experience, especially related to ERTMS. He graduated at the Technical University of Braunschweig as a mechanical engineer and got his PhD in mechanical and electrical engineering with his thesis on functionalities of ETCS. He was a major contributor in building the DLR ETCS test laboratory rail site, and he holds several railway system patents and more than 50 railway-related publications. He is also an alternate member of the Europe's Rail Governing Board and the chairman of the steering board of ERTMS accredited labs since 2012. Since 2012, he is also a fellow of the Institution of Railway Signaling Engineers. So thank you very much, Michel, and the floor is yours.
Thank you very much, Judith, for this kind introduction. It really sounds impressive. So I just sent the CV to you, and well, I have a lot of roles, and now I have again the situation that I have to introduce myself in a second role here, because I'm the work area leader of the KPI integrated assessment, and in this role I will be the next speaker, and therefore we can safeguard some time because I do not need to repeat my own CV. I will give you an introduction into the KPI model. Afterwards, we will have a second part looking into the customer experience model. So I will make the handover to my colleague Antoine later on. So I will go with you through these points in the next, let's say, 15 minutes, giving you a rough overview about the models we have in Shift2Rail. Antoine will refine that a little bit. I will tell a little bit about the methodology. It was a long project, Impact 2, which is still have a couple of days to run. So in Sylvester this year, we will end up. And therefore, the work I'm presenting to you here is really in the final stage. So we're just doing let's say, the spelling correction of the final report at the moment. Therefore, I'm happy to present the results to you, which Carlo mentioned already this morning. I will give you a short insight into the model, and I will give you an insight in the quantitative results and explain a little bit, and we will come to a conclusion and perspective later on. So maybe we can go to the next slide. You see here on the left-hand side the overall idea of the impacts of Shift2Rail, and on the right-hand side you see 3 boxes: the KPI model, the customer experience model, and the mode choice model. And the 3 models, as I said, Antoine will show you a little bit more details on that. I'm starting with the functional KPIs with respect to cost reduction, with respect to punctuality increase and capacity increase. And these are 3 parameters which can be described relatively technically, showing, let's say, really technical or economic features of the rail system. The customer experience is already a little bit focused towards the human being and the customers using the system. And at the end of the day, whether really someone is using the train or not is described in the mode choice model, which is not subject of the presentation this year, but there are a couple of publications. So if you're interested in this relation between the 3 models, you find a lot of publications inside the reports of the Impact 2 work package 4. So let's continue to the next slide. So we have a common approach, which, well, if you look on it from a distance, it looks relatively simple. If you look on the details, it's not that simple anymore. So we have what you see on the right-hand side 4 system platform demonstrators, so-called SPDs. And simple, this is a kind of scenario-based approach. So we have a high-speed scenario, we have a regional scenario, we have a metro scenario, and we have the freight scenario. One of the speakers before, Jürgen, mentioned already the SPD4 for the freight scenario and gave you some details into the other SPDs with respect to the energy consumption. And our approach was that we modeled simple baseline scenarios, which were quite generic. So for a reason, we didn't take some specific European scenario because they're all having specific inputs from the national rules, from the history and so on. So we designed something completely, I will not say on a white piece of paper, but we designed a very generic scenario and collected the data input for it. Then we applied the Shift2Rail innovations for them for a future scenario and put the improvement coming from the different IPs on these scenarios. Looks simple. What we need to acquire is much more than 400 individual input data and more than I think 200 improvement values. So we have very, very much data to be collected, and we always need to ensure that they're in a certain sense compatible or coherent, which was an interesting exercise. I will not go deeper in the details of this exercise, but we made a very, very complex, let's say, spreadsheet calculation on all these data, on the distribution of cost for some elements of the rail system. So this was a common approach. Then we need to become specific for the individual parameters, and this will be shown on the next slide. So yeah, thank you very much. So you see here we have the three parameters. So the life cycle cost, the capacity, and the punctuality on the left-hand side. So one important question to start with is, what do they really mean? So if we speak about life cycle cost, what is really meant here? How do we calculate them? How do we get the values for it? And you see here already that we identified for passenger and freight that there are slight differences. So for the passengers, we reduced the LCC to the, let's say, the main trip. So we don't care about how the passenger comes to the train station and how the way from the home door to the train station is done. We just say we care about the life cycle cost of the passenger train, of the CCS system, of the infrastructure and the operation, including energy. That is the parameter Jürgen showed to you coming out of the OPEOS model. So we have a link between the FINE 1 and OPEOS work up to the impact 2 world with respect to the energy calculation. In other words, we received input values from FINE 1, which were done with the OPEOS tool. For freight, the sequence is a bit longer, so we look there as well on terminals and yards and the related assets. We look again on the infrastructure, the CCS, including energy, the loco, the wagons, and so on. With the small difference that for the passenger trains, we always looked on multiple units. So we took them more or less as one fixed unit, which is separated by for maintenance purposes, but not operationally. For the freight train, we assumed that the trains could be split up into wagons and locos, and therefore we need to look a little bit in detail. You see here already, okay, this can't be done with one calculation, we need to have two. So we split up in two different models. For the capacity, well, simply you expect the same happened. If we speak about capacity for passengers, we somehow speak about passengers traveling somewhere. So we have a number of passengers per metric ton of the train. So if the train becomes lighter, we could have more passengers inside there. We have the track capacity in numbers of train per peak hour. So if we have, let's say, I will come to the technologies later on, but if we have, for example, ATO and moving block, we can have one train more in the peak hour, which is already a lot. So if you increase the number of trains from 12 to 30 or from 15 to 16, it's a lot of more passengers you can transport. And there is a last and third bullet point. If the coupling procedures of the trains in the stations could be speeded up, then we have more capacity because the waiting time in the station becomes shorter. So these three parameters involve very much the passenger capacity. For the freight, it's again a little bit different because we assume that the train can change its shape, so becoming longer, can become heavier. So we have wagons with increased load per wagon train length, and we have well, simpler, longer trains. For the punctuality, it looks very, very much similar. So we have there the, so again, the question is, what is the parameter about? And it's about unpunctual trains. And we would like to reduce the number of these unpunctual trains by 50%. And but I go not deeper in the details here, but we have a little bit more influence parameters for freight. So let's continue to the next slide. So how do we did this? So we took all these mathematics, we did all the parameters, and well, for someone working in the scientific field, this sounds a little bit like tables. And this is exactly what we did. We took, well, quite simple, we took Excel. And we started what you see in the gray box here. So writing down some things like a cover page, history, decisions, sources, and so on. That's material just to be noted. And then we have the yellow, red, and blue part. And it's working in this sense. We have the input parameters, which are designing the baseline scenario, the distribution. So how much is, for example, the CCS of an entire infrastructure? The improvements coming from the different TDs from shift to rail. And finally, on the fourth sheet of the input side, the accuracy level. So how precise are the different parameters? Are there expert estimations? Are they done by simulations, by calculation, whatever? Or even coming up from real operations. So this is the input side. Then we have 6 sheets of calculation. So simply for each KPI and passenger of freight, one page calculating the input. And we have one simple page showing called the overview page that's giving the result. We see this on the next slide. So if I may ask you to go to the next slide again. So, okay, this is what we use on the input side. So we have the input parameters. As I said, we describe the baseline scenarios for all 4 SPDs. We have the distributions, which are the percentage share of the total values for, especially for the cost on the elements of the train, on the elements of the CCS, and so on. We have the improvements, which is, in fact, what is the impact of the different technologies, the innovation coming from the TDs, and the accuracy levels, which I said already is the level of accuracy we have from expert estimation up to things like calculations, simulations, real operation. So now on the next slide, we see how it looks like. Oh, sorry, again. So I think I explained this, so we can forward to the next one already. So we have the overview sheet. The overview sheet is more or less, let's say, the user interface. So you have a drop-down menu where you can select which SPD you would like, and then you see a couple of fields and a couple of results coming out. They are shown in the context of the overall calculation, as well as the specific calculation for the IPs 1, 2, 3, and 5. You may ask why IP4 is missing here. The IP4 is looking on the customer experience, especially on the customer IT, and that's exactly what Antoine will present in the next presentation. So for IP1, 2, 3, and 5, I will give you the answer right now, and for IP4, Antoine will give you the answer in a minute. Okay, let's go forward to the next slide. Exactly, here we have it. So on the left-hand side, you see the selection. So SPD1, the high-speed one, is selected here. And then you see the more complex table on the right-hand side. The overall results are in the first green rectangle and for all the IPs. So you see it's 21% reduction for the LCC, 35 on the punctuality, and 75.6 for the capacity. Maybe these are outdated values, so it's just take them as an sample. Then we see for the individual IPs, so IP1, 2, 3, and 5, directly on the right-hand side, the values for it. You see already on the first glimpse that there's nothing for freight, which is not surprising as we speak about a passenger high-speed scenario. And you see how the individual values are compiled. They're not simply added up, so they're calculated by a more complex model. So as you see, there is a 35% increase in the punctuality. It's not simply adding up 7% and 3% and 18%, so that would be much less than 35. So there is, in fact, a combination of both. And in the green rectangle below, so the lower one, you see how the improvement is against the baseline of the individual IP. For example, let's look on the command and control system, and you see the cost reduction is approximately 1% there, which is not that much related to the entire scenario. If you look below, with respect to the baseline, with the individual baseline for the signaling system, it's a cost reduction of 15%, which is, well, it's still below the value expected by the program, but it's much higher than the overall value. So this is how it looks like. In fact, it's a very complex Excel model we have there. And this is what we have implemented over the years and filled, populated with a lot of data, with a lot of specific data for trains, for metro trains, and so on. Now you may ask me, how is the result at the end? And this is what I showed to you here. So that are the overall values. So the ones from the left-hand side, small green rectangle. If we look on the first SPD for the high speed, we have a reduction of 20% in the cost. We have a capacity increase in 58%, and we have a 39% increase in punctuality. Expected from the master plan initially was a 50% reduction of the life cycle cost, a doubling of capacity, and improving the capacity by 50%. See, we not fully reached these values, but we're in an order of magnitude, which is not let's say, by factors away from that. If we look on the regional train, it looks again a bit better. So we have not a 50% reduction in cost, but almost a 30%. The capacity is almost doubled. The punctuality is even better than only 50%, so we're at 55%. If we look in the metro system, it's a very, oops, sorry, okay, let's continue with that. So I don't know to go through each and every value, so it's okay. So let's go to the next slide. So if we look on the key effects, what have contributed here? So what we saw for the trains, it's the functional open coupler, which allows a lot of reduction, especially in the fleet size. So as trains can couple freely among each other without taking care about what supplier is delivering them, and helps to smoothen operation. For the punctuality, it's mainly the improvement of reliability of the traction system and the TCMS. In the signaling system, everything is very much, let's say, connected to each other. So it's very difficult to say what is exactly the impact of moving block of localization or so. At the end, the big impacts are coming from moving block ATO and TMS, but the other technologies are enabling those, so therefore it cannot be directly, well, appointed to one of the values. For the IP3, it's a condition-based asset management with better planning, with better supervision, which brings a lot of positive effects on cost as well as on the capacity. For the freight trains, it's the increase of payload, clearly, and we have the improved loading factor and the better punctuality due to digital management processes, which is, again, something improving very much on the positive side. So now I'm coming to the conclusion and perspective. So we have developed a very powerful tool here to show the impact of innovations on shift-to-rail, coming from shift-to-rail on the rail system. We have made an open model structure so we can adapt it to other assessments for other systems and representing the railway system. Nevertheless, some priorities need to be adjusted. So we were in a pre-Ukraine war phase, and therefore the energy costs were understood as the ones before. So now priorities will shift a little bit, and this is not reflected there. We are happy that in Europe's rail, an even more refined, even more detailed approach for the KPIs will be used. And so therefore, the model will definitely not apply one-to-one, but we are happy to input our knowledge and bring in all the developments from Impact 2 into Europe's rail. So thank you very much. We will have it as in the other work area discussion so that we have a common question and answer session at the end. I will now switch again from, well, I'm speaking anyway all the time, but I will switch from speaker to moderator again and introduce to you my colleague Antoine Verrier from SNCF. He's responsible for the activities in the customer experience model in the work area 2. And he is working at the SNCF group. He's currently in charge of managing the public funding grants. He worked for several transportation projects in the past already, not only in rail transport, but as well for air transport and other transport systems. And so he's very good in valuing the innovation coming out of these different projects and understanding especially how our valuable colleagues from aviation are calculating their KPIs, which have even a longer history in doing these kinds of model, and looking especially on the combination between KPIs and customer experience. So he was the perfect person to start this activity in bridging the gap between the mode choice and the KPIs with the customer experience model. So Antoine, I would like to hand over to you. You have the floor.
Yeah, good afternoon. Good afternoon, Michael. Good afternoon, everyone. Thank you for the invitation. So I'm Antoine Verrier from the SNCF Group, and I'm gonna focus my presentation on the customer experience model, which is complementary to the previous presentation made by Michael. So can we move to the next slide? Yeah, so this is a detailed picture on how the different models that were developed within the Impact 2 project interrelate with each other. So in red, you can see the KPI model that Michael has presented you just before, and which focuses on the 3 high-level KPI, punctuality, capacity, and life cycle costs. And this model fits the mode choice model that you can see in green on this chart. And my presentation is going to be on another model, so the one you can see in blue here, and that mainly upstreams the data coming from IP4, IT solutions, and also a few data from IP1 on rolling stock and IP3 on infrastructure. The customer experience model compute input data from these different IPs and then aggregates them all together so as to upstream the aggregated variables into the mode choice model. So next, Yeah, next slide, please. Yeah. So in order to assess the customer experience improvement over time, thanks to the different Shift2Rails projects, we had to make a few hypotheses to take into account the framework in which we are working with. First of all, we want to assess customer experience in use cases that do not exist in real life, and therefore we have to set a theoretical framework to assess customer experience in. Then we have to be able to upstream improvement values year after year so as to show the improvement that has been made. And therefore we have to work with relative values. And by relative values, I mean we have to assume that customer experience has a given number before Shift2Rails innovation and another number after Shift2Rails innovation. And therefore, we took the hypothesis that the customer satisfaction was at 0% on baseline year 2013, and that it would reach 100% once all Shift2Rails projects are completed and their innovation fully deployed. So this is how the model works, from 0 to 100, and all the data are computed in relative values only. So on this slide, you can see the two workflows that we have been developed so as to make the customer experience model works. So on the first workflow, you can see how we deal with the data that we upstream as an input. So first of all, we had to make a very long list of on the previous slide, please, was made by gathering data from a lot of Shift2Rails projects. And this helped us to build reference scenarios. The second workflows is about connecting the different Shift2Rails project outcomes with the improved scenarios. And we made use of a very detailed Excel file to combine these two workflows all together and to upstream the improvement values. So next slide, please. Yeah. So to make the model works, we have three different data sets. So first of all, there are the input data. So this input data gather over 250 different barriers that impede customer experience. Then we have the distribution values that allows us to weight the input data and to aggregate them into big packages so as to reduce the number of different variables. And then there are the third data set, so the attractiveness improvement. And these data come from the TDs leader that we get value year after year to assess the completion rate of Shift2Rails projects. So now we can move to the next slide. Yeah. So this slide is to give you an overview on how the customer experience looks like. So it takes the shape of a huge Excel file with many tabs. So on this slide here, you can see a few of the input data. So it's a list that was made by gathering the input of previous projects. So everything is properly charted, where the data comes from, what it relates with what IP of Shift2Rails, and so on. And now you can move to the next again. Yeah. The input data are processed following several steps. So first of all, we have the raw data coming from the previous projects, such as NEAR 2050, Go4Rail, Impact1, and some others. And then we make and we call this data elementary barriers. So this is a kind of label that we use for Impact2. Then we make groups of barriers, and these package are called AMPI. So this is some kind of word that you can see if you read through the Impact2 project's deliverables. AMPI stands for the big package of barriers. And we have around 20 AMPI, so 22 in total, which allows us to handle the whole data set much easier. And in the model, there is always a direct combination between the different level of grouping, so that it's always very easy to know what AMPIs deal with in real world. So what it really means. So now we can go to the next again. Next slide. Yeah. So on this slide, you can see a summary of how the input values and the distribution data work with. So on the left-hand side, there are the input values that I've just speaking about. And then we made use of other projects, other deliverables from other projects to weight these different input according to customer point of view. And therefore, we had to make another few hypotheses. First of all, the different data sets that we work with sometimes do not focus on the same customers type. They may have different age, they may have different background, different culture backgrounds, and so on. So we had to dress the picture of a standardized customer so that we could work all these data sets across. So therefore, we made use of Smarty, Find1, First Stations, and we also had to organize a workshop with the IP4 TD leaders so as to weight the different AMPIs related to IP4 accordingly. So we can go to the next again. Yep. So now I'm moving to the improvement values. Every year we go to the IP4 TD's leader, and we need to obtain from them the completion rate of their different TDs, and this helps us to get the improvement values of Shift2Rail and to assess by how much year on year the customer experience has improved. And on this chart you can see the 2022 improvement values. So at the beginning of this presentation, I said that customer experience would reach 100% by the end of Shift2Rail's project, and obviously it's not 100% yet because the improvement values were gathered during August 2022, and several projects were not completed at that point in time, and some of them will be completed only mid-2023, and therefore some of these data are still below 100%. But it's fine, it's not an issue. So now we can move to the next again. Yeah, so this screenshot is what the improvement data looks like. So we multiply, so to say, the improvement values by the distribution data, and this allows us to get what AMPI has been improved by what percentage, and by combining all these percentages and all these AMPIs, we get an overall value that allows us to say, well, for the three big packages of barriers that you can see here on the left, improved comfort and services, booking and ticketing, and improved information, the customer's satisfaction has been improved by X%. So as of now, the customer experience has improved by 30% if you should take into account all AMPIs, even the one that do not relate to Shift2Rail, because customer experience may also be impacted by a factor that do not relates with Shift2Rail's innovation. If we only focus on Shift2Rail's project, then the customer experience has been improved by 60% at this point in time. And for the IP4 that specific to the AMPIs that specifically relates to IP4, we have already reached 90%. And these are average values because we've made we make differences between the three SPDs, the three different use cases that were presented before. So now we can go to the next. Next slide. So I will go very quickly on this one because this slide shows how we gather the MPI, so the second level of grouping, into the three very big variables that are upstreamed into the mode choice model. So this is more for information, and I will move to the next again. Next slide. So as a conclusion, the customer experience model allows to fill a gap that was assessed at the beginning of the Impact 2 project, which was what's about the demand side, because the previous models focused on the supply side, on infrastructure manager and railway undertakings point of view, and the demand side, so that the improvement for the customers, individual persons, was missing on the chart. So this was a gap that has been filled by the customer experience model. The next step would be benchmarking similar model that could have been made for other industries. As for our previous contact, we have been surprised to discover that, as far as we know, there is no such model that would have been developed, for instance, in Clean Sky or in the other DUs. And we were willing to bridge the gap and get in touch with stakeholders from these industries, but for some reasons, either they were not willing to share their models or these models simply do not exist so far. And maybe for what specifically relates to the current model, so there is a need to keep it updated. So the Impact2 project has the right name, but it would be a very useful task to keep it updated with the coming deliverables of the projects that are not yet finished and that will arrive by the end of next year, to keep it updated. I thank you for your attention.
Thank you very much, Antoine. Thank you very much, everybody, for being here. So I think we're starting now well, thank you very much first for you, Antoine, and I think we start now the question and answer session. I'm looking in the chat whether there are any questions, or maybe there's a question from your side, Judith.
Yes, thank you. Indeed, I don't see any question from the audience, but maybe because this is a very relevant topic. So if you allow me, that if you could explain that, can you explain the difference between the freight and the passenger scenarios, how they have been defined in the KPI and why they were taken differently? And what is the advantage of having these two scenarios separated? If you could explain a bit on that, Michel.
Yeah, with pleasure. In fact, if we're looking on the evolution of the work, we started initially with having the models as close together as we could. Initially, we thought we need to separate a little bit the capacity model, but the two other ones could be identical. But it turned out that there were some nitty-gritty details which really makes it important to have a separate view. Let me explain this on the LCC model. So as I said, for the passenger model, we just simply reduced the LCC from a position where a passenger is jumping into the train or entering a train until an end station. So we don't care so much about the question whether the train needs to be stabled somewhere in between, how these stabling areas are operated. We just look on the main course or the main run of the train. It turned out that this would reduce the freight model beyond some things which were discussed inside Shift2Rail. For example, the alternative drives for shunting locomotives or the digitalization of procedures. So therefore, we came to the understanding that that at least the cost models need to be different, and it turned out that this is valid for the same, or in the same sense for the other parts of the model as well. So for the capacity, we discussed with the colleagues from the passenger trains, and they said the overall frame of the train, so length and weight and so on, needs to be the same as before. So we were much more limited in the things we could expect to and the difference to the freight model. So the freight model allowed us to have heavier wagons or longer trains, which was not foreseen for the passenger trains due to various reasons. And the last one, so the punctuality model was the last one, which was split up. Again, as we identified that for the passenger, the important things are happening during the run of the train. So we assume the train is ready there in time, at least in the morning for the first start, and then the train is just running and the delays are coming out of the operation. While we identified for the freight model, the delays are coming a little bit from the outside. So we again need to split up the models. And at the end of the day, we're not so happy in having really two, let's say, different universes of models for both scenarios for the passengers and the freight. And this is one of the points where we see further space for the research. You see, there are several countries in Europe, especially Germany is one, where you have mixed traffic between passenger and freight transport. And then saying, okay, we have just a separate KPI evaluation for passenger or for freight, but they're not combined, doesn't give justice to the real world outside happening on the rail tracks. So therefore, we know that there are some, let's say we oversimplified some things to get an answer at all, but it's clear there is further work to be done. And what we are looking forward in Europe's rail is to see how we can, let's say, deepen this knowledge about the system and having this story widened a little bit. But let me come to one point. It was not 100% related to your question. So this combination of the KPI model looking very much on the euro and the technology, and the customer experience model looking on a completely different methodological approach, and again the combination with the mode choice model looking on the persons choosing a freight train or freight transport or passenger transport for something, is something which we didn't find that in this complexity in the literature. So we made, from a methodology point of view, a major step forward here inside Shift2Rail in combining modeling approaches which were completely differently focused on different aspects of the overall ecosystem of rail towards an integrated model. So I'm quite sure there are a lot of things which we can improve in the detail, but the overall line is something which is really unique and not done before in this, let's say, complexity.
Yeah, thank you, Michael. I think indeed what is your last point is I would like to emphasize it, that also when you are talking about the customer experience model, the work that has been done to identify the different barriers, the different areas which impacts the attractiveness of the customers, passengers to take one more on another, it's very relevant. And then understanding their needs is key in order to ensure that we can provide a service that is up for the current people's needs and requirements. And this is essential in order to attract more clients for the rail sector. Thank you very much. Yeah. So just to summarize, thank you also Antoine and Michel for the presentations. So now we are coming to the end of the cross-cutting activity session. Just to summarize, I think it also shows the importance that what was mentioned already in the keynote speech of Carlo and Giorgio, that when we are looking at rail, we have to think of it as a system of systems. So we can optimize the railway system if we are looking at it from a holistic perspective, looking at all the different systems together and optimize them, rather than not only focusing on the separate areas. So this was the strength of the CCA activity, that looked into the whole system in one, which was also the challenge as well, because all this information and data and alignment with the other innovation program made the exercise very interesting, and collection of information that was fed into the activity was essential. Also, when we are looking to the KPI model that was now presented by Michel. Also, what I would like to say that we could see in the energy work area already a significant improvement that can be done, but we have to look into the future. So how the EU Rail program can bring further improvements and make the system even more energy efficient. This is what we need to look into, and again, not only at one specific subsystem level, but looking at an overall system. So all these activities show that the railway system is very complex, but we can make significant improvements if we work together. All the experts from the different areas are collaborating and bringing their knowledge into this collaborative research activities. So I would like to thank to the speakers and also for the CCA experts for the work that has been done in the last years, and during this session that you have presented the good and interesting results of the Shift2Rail project. I also would like to thank to my colleagues here in the studio who supported us in the background in order to make this session happening and as smooth as possible. And I would like to now give the floor to the closing remarks to Giorgio Travaini and Katrin Cesco. who are going to close today's innovation section. Thank you very much for your attention and wish you a nice evening. Bye-bye.
Good afternoon, everyone. I'm very happy to be here today with you. I am Catherine Chesco, Chief Stakeholder Relation and Dissemination at Europe's Rail. And I'm very glad to be contributing to this first Innovation Days under Europe's Rail, and to close this first day with my colleague Giorgio Travaini, who's our head of innovation programs. We will give you a little summary of what has been happening today and what will happen tomorrow. We had a very interesting opening session this morning with our executive director, Carlo Borghini, and Giorgio. This gave the opportunity for us to be reminded of the importance of rail in the objectives of the Green Deal. It was also the perfect opportunity to highlight again how much rail can actually address also the energy crisis that we are going through at the moment. This morning was also a perfect occasion to announce the first signature of the first grant of Europe's Rail. So we're very happy to see that the program is actually kicking off as of yesterday. To summarize this morning, we actually had the opportunity to have two sessions today. One was devoted to passenger trains, and the other one to cross-cutting activities, which we just finished right now. And interestingly enough, one of the topics of the cross-cutting activities addresses the issues of energy crisis. So perhaps, Giorgio, you would be kind enough to share with us a few of the outputs of the sessions from today.
Yes, thank you, Catherine. And well, thanks also to all of you that are still here listening to us. I know it must not be easy at this time, but well, we're used right now to this type of events. I would like just to sum up a bit on the results that you heard already this morning on IP1, but not on everything. It's just the fil rouge that we decided to have with these innovation days this year. And the fil rouge, as Catherine also highlighted, is the energy optimization that we can make thanks to the activities that we have been conducting already in Shift2Rail. We've seen, for example, that lightening the structure of the rail carriage, the trains, with lighter car body shells, and also with the running gear, it will significantly reduce the energy consumption. But not only, again, always the link to the user, especially when we're thinking of running gear. Everybody of us always love to take the train, because on the train we can work, we can sit comfortably, and it's a smooth run. But also there we can do better, and this has been demonstrated with the demonstration conducted in Shift2Rail that you heard this morning. In addition to that, we had the weight being, let me say, further reduced from the application of a single axle running gear. And this innovation are linked also, well, we need also to always look at the cost component, because we would like to have demonstration activities that later on are also implemented into the market. So the cost, of course, not only the cost of the innovation, because these most of the time is going to be more expensive than solutions that already exist, although I think we can still target a lower cost solution, but looking at the life cycle cost. So if we're able to demonstrate that in the life cycle cost, the cost of the rail system goes down, as Judith said at the end, it is a system of system, we can make also rail more competitive, and the work that has been done for the universal cost model is one way forward achieving that. And then the last point that we heard in IP1 It was about innovative doors and innovative interiors. And here, many people will say, okay, but these are really subsystems. Do we really need to do research and innovation on that? Well, the answer that from the output of this morning session is yes. Why? Because also those are key contributor, for example, to the thermal acoustic conditions of the train, if we're speaking about the doors, and this is linked to comfort, is linked to energy efficiency, but also accessibility. So we need to create the environment, including the interiors, that provide the best accessibility for all our future current and future users. And this is for the rolling stock. Then for the CCA activities of this afternoon, well, I think you're fresh in your mind about it, but I would like to put the focus on a couple of things. First, we have set the basis with some activities of the CDM with what I've been introducing this morning. For example, improve optimized traffic management system. In fact, the work being done with the canonical data model has shown that it is possible to optimize the freight. It is possible to optimize the management of the crew together with the management of the train. And this will ultimately lead to a better optimized system that will also, let me say, look into basically reduction the waste of operation, and therefore indirectly, if you want, to make a better energy efficiency overall. On the energy work area, well, this is the energy work area. So by definition, it was looking in an holistic approach to all the technologies that Shift2Rail have been working on. And you have seen significant possible improvements, but not only on complete new innovation, but also on innovation that have been already achieved in the past, but that are put to the correct use today. For example, like the driving advisory system, the more we're going to standardize those type of solutions, the more we're going to benefit overall as a system. And this also will be also linked with the work of the system pillar that also I mentioned this morning in terms of standardization activities. CCA also highlighted the new type of technologies where we can make a saving of energy. And this is always useful because, you know, I say sometimes you have the crystal ball when you read the multi-annual work plan in Shift2Rail, when you were reading the multi-annual action plan, but actually nobody knows the future. So all your research activities are helping us to make update of the multi-annual work plan. It's not written in stone. And also, more importantly as well, to define the content of our future call. So we urge you to tell us if something needs to be looked at. And then finally, KPIs. So the KPIs is essential for monitoring that we're going into the right direction. And obviously, we're going to take stock of all the work that has been done. And as showed to you, we're also looking into the societal business case, making use, for example, of the work done in CCA for the mod choice model, that it was looking also to the attractiveness of the rail system.
Thank you, Giorgio, for these very insightful outputs. Of course, now you've heard from us, but we would like to hear from you as well. So I would like to remind that we will be sending a satisfaction survey after these innovation days, which will be available on our website from Friday, but also will be sent to all participants from Tuesday onwards. But as we have a bit of time, by all means, if you have any contribution you would like to make at this point, feel free to send us your contribution in the chat, and we'll be happy to address them as we speak. And perhaps in the meantime, I will go through what will be happening tomorrow. We will start promptly at 9:25, so be ready for a kickoff at 9:30 with very interesting session that we will have on optimized infrastructure. After the lunch break at 1 o'clock, we will have a session dedicated to digital services. And to finish the day, we will have a session which will start at 3 o'clock on IPX, which will be focused on system architecture and disruptive technologies. The day will close at 17:30, and we'll come back with Giorgio to give you some final outputs of the sessions again tomorrow afternoon. So I don't know if there are some comments in the chat at this stage. Otherwise, perhaps...
It seems all is clear.
Voilà.
And I hope really that you enjoyed this session. We are there also to disseminate the output of public funds. Let's not forget about this, because all your work, of course, will serve the institutions and the companies that you are working for. But it is also for us important to show the good use of public funds, and this type of event, which are open to everyone, serve also to that. So also please invite your friends tomorrow to listen to the next innovation, please.
Have a good evening all, and see you tomorrow morning at 9:25. Thank you.